Hello, this video is on pressure volume graphs, and the essential question is, what can we learn about a thermodynamic system from looking at a pressure volume graph? So a pressure volume graph will usually have pressure on the y-axis as the dependent variable as a function of volume on the x-axis. For any closed system, assuming that these graphs represent always closed systems, any single point on this PV graph is going to be known as a thermodynamic state. Okay, so the point shown on that graph represents one possible state of my system, of my given system. So if you know the n, if you're given that in the problem, and you can pull P and V off of the graph, you can figure out lots of stuff about that system. You could figure out temperature because you can use ideal gas law. Right? PV equals nRT, and we know everything other than T, so you can find the temperature. If you know the temperature of a gas, you can figure out the average kinetic energy of the gas molecules using that Boltzmann's temperature energy conversion. Once you know the kinetic energy, if you know what kind of gas it is, then you can figure out the average velocity using the kinetic energy equation. You also could figure out U, and this ends up being the most important thing that you can figure out from that data point, the state, because U is going to be the product of the average kinetic energy multiplied by the number of molecules in the sample, which is n times Avogadro's number. So for any possible state, you can calculate what is the thermal energy given a point on a PV graph. So usually when you're given these PV graphs, they contain not just a single state, but they'll contain an initial state, usually a final state, and they'll have a line on there showing the path that the sample took to get from one state to the other. This path is known as a thermodynamic process. Thermodynamic processes happen when you either put heat or work into your system. So we know that the first law of thermodynamics says that you can change your U by heat or work, and U is characteristic of the state. So heat or work will change my state from one location on this graph to another, and it can go through a series of different paths to get there. Since U is characteristic of the state, the system's overall delta U, change in U, depends only on the states, the initial and the final state. It doesn't depend on the process. You can take any path to get from that initial state to that final state, and you're still going to have the same delta U. We call this path independent. So that variable is path independent. However, different paths involve different contributions of U and W, right? So we can get to that initial state. Since delta U depends on either U or Q, we can go from initial to final either through U or through Q or through some combination of them usually. And so the Q and the W will depend on the paths. Those are called path-dependent variables. So how do we find the values of Q and W from a PV graph? We've already talked about we can calculate U directly as long as we know N, which means that we can find delta U directly just from taking the data points. But how do we find Q and W? Work is actually really easy to find on a PV graph. If you have a lovely graph with a process, remember that work is defined as the negative pressure times the change in volume. So if you have this graph of a process AB, you could read the pressure off the graph, that would be the P right there, and you could find delta V from the graph if we know our initial volume and our final volume. And so you could calculate it directly by pulling data points off the graph if you wanted. Or you can take a shortcut, which is to realize that you've essentially described the area under that graph, right? The delta is the bottom piece of that graph multiplied by the height. So we have the width of that rectangle multiplied by the height of the rectangle. That's the same as the work. And so usually it's kind of conceptually quicker and easier to, instead of pulling data points off the graph, calculate work by calculating the area under any process. And so when I say under, I mean from that process line down to the x-axis. The one tricky thing about using the area under the curve process is dealing with that negative sign in the equation. So I usually just remember in my brain that we're always positive work if the gas is being compressed, and we're always negative work if the gas is being expanded. So if my states A and B, if I was going from B to A, right, that's going to be the gas being compressed, so that would be positive work. So moving to the left is actually positive, and then A to B would be an expansion as my volume gets bigger, and so that would end up being a negative work. So you got to kind of tack on that positive or negative sign after you calculate the area under the curve, because the area is always going to be positive. So you need to think intentionally about what your negative sign should be. You can use this area under the curve method no matter what the shape of the process is. If you're in calculus, you know, you're probably thinking integrals. That's what we're doing here. In this class, the most complicated shape they would ever ask you to figure out the work for would be sort of a thermodynamic process where we have a linear graph where the volume is changing in a straight line as a function of pressure, or pressure changing as a function of volume. So this would be really ugly to try to use the negative P delta V situation for. Well, not really that ugly, but P is changing, and so what do we do with the P in that equation? So for me, it's much faster and more accurate to use the area under the curve method, realizing that we have two chunks of that area with the green triangle and the blue rectangle, so you've got to calculate both of those areas. Or you can do the area of, is that a trapezoid? I kind of forget my geometry, sorry. But there's an equation for that too. It's basically 1/2 base times height is essentially what you're looking for to find the area for that. So in this case, you would do 1/2 base times height to calculate the area, and then you have to tack on your negative sign or not. If we are expanding, that's going to be negative work, so your area for this example should be a negative work. So now we know how to find U and hopefully delta U, because if you have two U's, you can find delta U, and we know how to find W. How do we find heat from our PV graph? Heat takes a little bit more effort. There's nothing direct or quick about finding heat from a PV graph, because you basically have to use the first law of thermodynamics. So you're going to find the work using the area under the curve, making sure you get your positive negative signs right. You're going to find delta U through combinations of pulling your data points off your graph and all those other equations as necessary, remembering that delta U is path independent, doesn't matter, but you do need your data points for the start and the end. And then you simply use the first law of thermodynamics to determine Q. So delta U equals W plus Q. You just have to subtract your work from your delta U and you get Q. So it takes all of those other steps in order to find heat from a PV graph. Which means they don't usually ask you to do it, but what they will often ask you to do is to determine whether that heat is positive or negative, and that should be quicker, okay? Because if you can determine the sign of delta U and you can determine the sign of work, often you can very quickly figure out whether heat has to be positive or negative from that. So the other thing that you often see on PV graphs is known as a thermodynamic cycle. So a thermodynamic cycle is a series of processes that are connected that eventually take a system of gases from one state through a bunch of other states and eventually back to its initial state. Because we know U is characteristic of a state, that means that the delta U for any cycle is 0. We end up at exactly the same thermodynamic situation as we started with at the end. So we have the same pressure, we have the same volume, we have the same N, we have the same U, we have the same temperature. Everything is the same exactly about the gas at the start and at the end. However, this does not mean that work or Q are 0 for a cycle. In fact, work and Q will never be 0 for a thermodynamic cycle. If you think about the first law of thermodynamics, if U is 0, that's fine. And Q and W can be not 0 as long as they're equal to each other, right? So a 4 plus a negative 4 is 0. A 90 plus a negative 90 is 0. So what we end up getting is work is equal to negative Q, or negative work is equal to Q, depending on how you write the equation, based on conservation of energy for any cycle. So functionally, what happens here is that running a thermodynamic cycle allows humans to turn heat into work out, or work into heat. And those are both really important for us. Like, we want work. We want machines that drive, for example, a car uses this exact technology to turn the heat of gasoline into work and push that car forward. We also at times want to be able to generate heat or separate heat. We use this in our refrigerator systems to take a motor that's moving and turn that energy into the ability to create heat or cold in different areas. So thermodynamic cycles are really, really important and useful in the real world. The area inside that curve, so the weirdly shaped blobby area inside that graph, is going to represent the amount of energy that is transforming from work into heat or vice versa. So if you wanted to make a really good car or a really good refrigerator, you want to maximize the area inside that graph because that's going to tell me how much energy is turning from one type into another. In order to figure out whether we're generating work or generating heat, you need to pay attention to the direction of the cycle. I'm going to walk you through this process. There's also just a shortcut to memorize, but let's start with figuring it out. So in this graph that we're showing, there are two processes, process 2.3 and process 1.4, that actually have no work generated. And the reason that no work is happening during those processes is because there's no change in volume. And there's no area under the curve. That doesn't mean there's no heat. There might be heat during those processes. In fact, there will be heat during those processes, but there's no work. So no W during those two vertical processes. So we just have to consider process 1.2 and process 3.4. 1.2 is an expansion. We're getting bigger. That means we have a negative work according to that equation. And if you look at the area under 1.2 all the way down to the axis, it's a large area. So I would say there is a large amount of negative work that happens during process 1.2. Process 3.4 is going to be positive work because we're a compression. However, it's going to be less positive work because the area underneath curve 3.4 is actually smaller than the area under 1.2. So you can see how we're sort of subtracting that bottom area from the top area, and that's why we end up with just the area inside as our relevant area. So anyway, we had more negative work from 1.2 than we do positive work from 3.4. That means this cycle in the direction that it's shown is going to have overall negative work. And because of conservation of energy, this means that this cycle must have overall positive Q. So this is a cycle that is you're putting heat into it, okay, that's a positive Q, and work is coming out. So this is like the car example. We're getting work out by throwing heat in. Now, of course, there's a shortcut you can just memorize, essentially. If your cycle is clockwise, that means my top process is always going to be my expansion. Clockwise cycle will always produce negative work and positive Q. Or counterclockwise, if your cycle ran the other direction, we would be reversed. We would always be producing positive work and negative Q for a clockwise cycle. I usually tend to just do it quickly myself by thinking about just that top process. That top process is going to be the one that kind of drives the overall work or Q for this system, because that's going to be the process that has the most area under the curve. So in any case, you need to be able to quickly and efficiently determine what kind of process are we dealing with and what are the signs on U, Q, and W for any process. Okay, we've reached the end of the video. The essential question is, what can we learn about a thermodynamic system from a PV graph? And the answer is a whole heck of a lot. So hopefully you guys can process this, make sure it's in your own words, and enjoy a little comic that I put on there for your reward. Thank you for watching.